Hello and welcome back. We will start section 2.7 in this video, which is all about inverse functions. These are a particular type of function, and I think it's easiest to see these with a picture. So when we think about a function f of x, I tend to think of this function as a machine. We've got our machine labeled f. And when we plug our x as an input into the machine, we'll get an output. In this case, the output is found according to the rule x plus 3. So you just take the input and you add 3 to it. So for example, if we plugged the number 5 into our function f, out the other side along the conveyor belt, we'll get an 8. Now, a sort of natural thing to do here would be to reverse this function. Would be to make a new function that whatever you would get out, if you put it back in, you get the input. So it's just kind of pushing this 8 back through a new function. So we'll call this new function g. And what I want this new function to do is when I plug in an 8, when it comes out the other side, I want to get this 5. So essentially I've reversed this machine here. And one such function that when you plug in an 8, you'll get a 5 is if we subtract 3. And when we think about our original function and what this function looks like, this kind of makes sense. If f adds 3 to a number, adds 3 to its input, if we want to go backwards, we might just subtract 3 to get back to where we started from. So let's define g as this function x minus 3. And what we'll see is that these functions undo one another. So when I hook these machines up, as in when I compose these functions, if I plug in x into g, what do I get? I get x minus 3. And when I plug that function back into f, I'm simply going to add 3 to it. So it'll be x minus 3 plus 3. But we can see that this cancels and we just get x back. So what we started with is what we end with. And they undo each other. Likewise, it doesn't matter the order in which we do this. We could do f first and then g, and we'll get the same thing. When we plug x into f, we're going to get x plus 3. And when we plug that into g, we're going to then subtract 3 from it, and x plus 3 minus 3 is just going to be x again. So these functions undo one another. And this is what we will call inverses. So let's give a formal definition for what an inverse is. So if we have two functions that satisfy the following. If you plug x into g, and then whatever you get then into f, we get x. Essentially, the actions of g and f have undone one another. So whatever you plugged in, you just got out the other side. Also, if we have to be able to do this in the other way, if we plug an x into f first and then into g, we should end up with just what we started with. Provided that these two things are true, then g is the inverse of f. Okay. We write, so we give g a name, so g is the inverse of f, and we write it like the following. G is f inverse. Now, note, this is not 1 over f. Even though we have something to the -1 power, this is not the same thing as a power. This is not f to the -1 power. This means f inverse. So it's very, very important that that this does not mean just 1 over f. Likewise, what numbers can we plug in to g? Well, anything in the domain of g. So this has to be true for all x in the domain of g. And then what numbers can we plug into f? Only those x that are in the domain And this is just a little bit of technical things. I can't plug, say, negative numbers into square roots. So if there's a square root anywhere, I just have to know that I can't plug a negative number in. And remember that the domain of a function is just all the things that we can plug in. So when we think about the relationship between the domain of a function and its inverse, well, what should we be able to plug into the inverse function? Well, whatever we can get out of f, so all of the outputs. So another way to think of this is that the inputs of f inverse are the outputs of f, and vice versa. So the outputs of f inverse should be the inputs of f. If they're going to undo one another, I have to plug what I get from one into the other. So let's go through an example. Let's show that these two functions are inverses of one another. So again, the way you do this is we're just going to check f of g of x. So again, we're going to apply g to x, and then we'll apply f, and see if we get what we started. So this is going to be f of g of x, and g of x is just going to be x plus 7 over 4. And then I get to plug it into this equation up here. So this is the input, so this is going to be 4 times the input minus 7. And there's a couple of things that'll happen right away. We'll notice that the 4 and the 4 will cancel, so that we have x plus 7 minus 7. And oh look, we get x. So if you apply g, which adds 7 and divides by 4, and then you apply f, which multiplies by 4 and then subtracts 7, we get what we started with. This is good. Next, we have to check the other way. There are situations in which one of these could be true but not the other one, so we do need to check both. So what we'll do is we'll first apply f, and then we'll apply g, and hope that they cancel out. So when we apply f, we're going to get 4x minus 7, and then we'll plug all of that into g. So we're going to have 4x minus 7 plus 7, all divided by 4. Well, the first thing we'll notice is that we're subtracting 7 and we're adding 7, so those are going to cancel out. And now we're multiplying x by 4 and dividing x by 4, so we just get x back. Both of these are true. They are inverses. Perfect. And when we look at these, we can kind of see that these will be inverses of one another. If we think about what happens to x as we apply f to it, well, so what does f do? F multiplies by 4, so we go times 4, and then we subtract 7 to get 4x minus 7. But what happens when we plug something into g? Well, we first add 7 to it, and then we divide by 4. And what you'll notice is that the order in which we do these things matters, but at every step we just cancel out. So the first one multiplies by 4 and then subtracts 7. The second, g, will cancel out the subtract 7 by adding 7, and then we cancel out the times 4 by dividing by 4. So we can see that these sorts of things will cancel out. So if I gave you a function, we can figure out what the inverse is just by essentially looking at what happens to these functions. And there is a rather straightforward process. So essentially, how we find the inverse of a function, if you're given a function, we will replace f of x with y. And if we want to undo one another, this is the important step here. We'll switch all of our x's and our y's, and then we solve for y. So I want to do an example of this, and then I'll come back to what happens down here. So we'll just look at a function. We'll replace f of x with y, and then switch x's and y's. So let's go through this example. Let's find the inverse of f of x is equal to 2x plus 7. So the first step, if this was my original function, I want to replace f of x with y. So I'm going to write down y is equal to 2x plus 7. So this was, we replace f of x with y. Next, I want to switch all x's and y's. So instead of y is equal to 2x plus 7, we're going to have x is equal to 2y plus 7. And now solve for y. So here, if I want to solve for y, I might subtract 7 from both sides to get x minus 7 is equal to 2y. And I can divide both sides by 2 to get, and then I'll move this to the other side, y is equal to x minus 7 divided by 2. Now, does this make sense? Our initial function multiplied x by 2 and then added 7. This function subtracts 7 and divides by 2. This makes sense. Let's check and make sure. How do we check? So if this is my function, what I want to do is I want to write this as f inverse of x is going to be equal to x minus 7 over 2. So let's check. Let's plug x into f inverse, and then we'll plug that into f. So my formula for f inverse is x minus 7 over 2. And my formula for f is to multiply by 2 and then add 7. So we're going to multiply our input by 2 and then add 7. Well, 2 cancels and 2 cancels. So we get x minus 7 plus 7. And minus 7 plus 7 cancel. We just left with x. Perfect. Next, we should check the other way. F inverse of f of x. So we're going to first plug plug x into f. And our formula for f is 2x plus 7. And when we apply f inverse to this, we're going to get 2x plus 7. We subtract 7 and then divide by 2. Well, 2x plus 7 minus 7, that's just 2x. And 2x divided by 2x divided by 2 is just x. And voila, we've come up with the inverse. And we've checked to make sure that it works. Now, there is something that can go wrong in this process. After you switch x's and y's, you may not be able to solve for y. So sometimes it's impossible to solve for y. That means that this function has no inverses. And this is also the reason why we want to check that the inverse that we found is actually the inverse, to make sure that we didn't do anything wrong. So what I'll do is I'll go through an example of a function that doesn't have an inverse, and in the next video I'll go through an example where we stumble across that. So this is an example of a function without an inverse, and let me explain why. If we think about this function that takes the absolute value, if we plug in a 1, the absolute value of 1 is just 1. Okay, that's pretty straightforward. But the absolute value of negative 1 is also 1. Now, the problem with this function, as concerning its inverse, is if we wanted to find an inverse function, we have to go backwards along these routes. So if we plug in a 1, what do we get? A negative 1 or a 1? There are multiple ways to go backwards from a 1. And a function, you can't get two outputs for a single input. when this happens, there is no inverse.